So the next topic we're going to be looking at in stoichiometry involves formulas. We're going to talk about empirical and we're going to talk about molecular formulas. Empirical formulas may or may not actually exist, but they are representing the simplest ratio of the elements that are present in a given compound. So I've got two examples for you that both share the same empirical formula. We have glucose and we have formaldehyde. They both show a 1 to 2 to 1 ratio of carbon to hydrogen to oxygen. So in this case, the empirical formula actually does exist as a true compound, but there are times when you will have empirical formulas that do not necessarily represent actual true formulas. They just show that skeleton, the basic ratio of the elements present in that chemical formula. So when we want to figure out what an empirical formula is, we either have to be given masses of those elements or we have to be given the relative ratio of those elements in the compound, usually by percent composition. We can't compare grams of elements to one another, but we can compare moles of elements. So we use the molar mass of those elements to determine how many moles, relatively speaking, we have of each of the elements in our compound. At this point, you may have fractions, you may have whole numbers, but we haven't really looked at how the moles relate to each other in terms of the elements making up your compound. So in step 3, we take the moles that represent the smallest number of moles for the elements that are present in your compound, and we divide all of the moles of the other elements in the compound, as well as that element, by the smallest number of moles. And at this point, you should be getting pretty close to either whole numbers or to ratios that represent pretty common fractions, like 1.5, 2 1/3, 1 3/4. And if you do get a fraction, we can't just round it up or round it down. These are representing the relative ratio of elements present in our chemical formula. So we want to make sure that we take care of those fractions by turning them into whole numbers and multiplying them by what their denominator would be as a fraction so that we can make them all be integers. And what you do to one of the ratios, you must do to all of them since they're all in comparison to one another. Those ratios would represent the subscripts showing us the basic skeleton, the basic structure of that particular chemical formula. So I know that was a lot of steps. We're going to do a couple of examples, and I hope that's going to help, and then we'll do some more in class. Here you have the empirical formula that's got 58.80% barium, 13.75% sulfur, and 27.45% oxygen by mass. So if we had 100 grams of this compound, 58.8 grams of it would be barium, 13.75 grams of it would be sulfur, and 27.45 grams of it would be oxygen. So that gets us our starting point. We have grams being represented as those percentages of each of the elements making up our compound. Again, since we can't compare grams to one another, we're going to move on to step 2 and convert these to moles using the molar mass of each of these elements. Notice with oxygen, I did not write it as a diatomic element because it's not truly by itself, it's part of a compound. So even if you have diatomic elements making up one of your masses or one of your percentages, you still want to treat it as a monatomic element as you are trying to determine how many moles of this element is present in your compound. How many moles are present, excuse me, bad English. So at this point, I'd go ahead and do my division and get my moles for each of my 3 respective elements. Again, these right now are still not going to serve as our subscripts in our chemical formula. We need to set up ratios so that we can compare the elements to each other. And we do that by taking the molar amount or the moles that has the smallest number attached to it, which one is representing the fewest number of moles. And that would be barium. All of them would be divided by 0.4282. And when I do my math through for this, I get 1 mole obviously for barium, or the ratio would be 1. Sulfur is super duper close to 1. And the ratio for oxygen is super duper close to 4. You may notice I did not round off my mole amounts a great deal. I look at my sig figs for my molar masses and my sig figs for my starting value for the different elements, and I want to keep at least as many sig figs as the value that I'm starting with that has the fewest sig figs. If you round off too much, it can throw off these ratios, so please take care not to do that. At this point, you have what the elements' ratios are compared to one another, and those give you the subscripts that make up your chemical formula. You have one Ba, one S, and four Os in making up this particular chemical formula, barium sulfate. This is not a formula that could be simplified, so that's why this would actually be a true formula. And I don't expect you to recognize a formula by actual or if it's just a theoretical empirical formula. I just want you to be able to use the information given to be able to determine what the potential empirical formula would be. This time I'm giving you masses. You have 52.9 grams of aluminum and 47.1 grams of oxygen. We're going to calculate the empirical formula for this compound that just has two elements present. So again, we start with our grams. We convert our grams to moles. That gives us moles of aluminum and moles of oxygen. The one that has the smallest number of moles is the one that I use to set up my ratios, the 1.96. Aluminum's ratio is obviously going to be 1, and oxygen's is actually more close to 1.5 than it is to 1 or 2. You can't round off fractions once you get to the ratios because what this is telling me is that for every 1 aluminum that's present in my formula, I need roughly 1.5 oxygens. I told you all that if you have a fraction, you're going to multiply by the denominator to turn it into a whole number. But what you do to one of the ratios, you must do to all of them. So both ratios get doubled, which gives me 2 aluminums and 3 oxygens. And that might look like a formula you've seen before between aluminum and oxygen. The half is pretty much the only ratio you all are going to pretty much encounter in your practice. There are other ratios, but I don't tend to see any more complicated ratios than the half. So just keep in mind that if you do end up with a fraction, that again, most likely it's going to be a half, and that you have to go back through and turn it into a whole number. If you get a ratio that is less than 1, you probably did not divide by the smallest number of moles to begin with. So now we're going to see how we can use these empirical formulas to determine molecular formulas. How we get empirical formulas is in part, there's just different analytical devices that can tell us the relative ratio of elements present in our compound, and that can give us that percentage data. And then there's also devices like the mass spec, where you can get the actual mass of your compounds. So if you know the skeleton and you know that the skeleton has to be the molecular formula has to be some multiple of that empirical formula, you can use those two pieces together to figure out what the actual formula would be. Because your molecular formula is some multiple of that empirical formula, the subscripts that are present in it. So to find a molecular formula, you need to get an empirical formula, and you need to calculate the molar mass of your empirical formula, because if they are multiples, they should be some ratio of one another in terms of mass. The molar mass of the molecular formula, you don't know unless it's given to you. I'd have to either give you that value or give you a range that you could pick that would work with the empirical formula's molar mass, and that you could use that to get a guesstimate as to where your molar mass falls. We can calculate the relationship between the molecular formula and the empirical formula by dividing their two molar masses. We know that the molecular formula should either be at a minimum the same molar mass as the empirical formula or some multiple of it. So these should always be really close to a whole number. Once we get that whole number, we can then multiply all the empirical formula subscripts by that value to get our molecular formula. So here we have a white powder. It was analyzed and determined to have an empirical formula of P2O5. We're told that molecular mass, the molar mass of the actual compound is 283.88 grams. What is the actual molecular formula for this compound? So we have an empirical formula, P2O5. And we can find the molar mass of that, 2 times 30.97 plus 5 times 16, and that gives us a molar mass of 141.94 grams. The problem told us what the molar mass of the molecular formula was, approximately 284 grams. So now that I have that piece and I know the molar mass of my empirical formula, I can calculate N by dividing the molar mass of the empirical formula into the molar mass of the molecular formula. And you get that this is super duper close to 2. This one might be right on 2, but generally speaking, they are going to be super close to a whole number. So what this is telling me is that my molecular formula is roughly twice the size of my empirical formula. So if I take my subscripts in my empirical formula and I double them, I can get what the actual true formula would be for this particular compound, P4O10.